This video is an overview of the Cal Poly Gust generation system installed in the university's low-speed wind tunnel. During this video, the components of the Gust generation system will be introduced and their specifications and performance will be demonstrated. The Gust generation system in its current configuration is capable of generating sinusoidal gusts of up to 4.5 Hz with a maximum gust vane deflection of 12 degrees. The addition of a vector duty motor will enable the Gust generation system to generate gusts at up to 14 Hz. The Gust generation system also carries a full sensor suite, which is used to measure the performance of the system as well as characterize the gusts being generated. This Gust generation system, when combined with the university's 5 degree of freedom sting mount, allows for wind tunnel models to be flown within the wind tunnel and the gust response of each model to be studied in detail. At the conclusion of this 5-year research effort, the university will have the capability to test free-flying wind tunnel models with fully aeroelastic wings and flutter suppression control laws. Let's take a look at the components and capabilities of the Gust generation system in detail. The gust vane system is controlled through the use of a variable frequency drive connected to a 5 horsepower AC induction motor. The motor is connected to a 10.85:1 helical reduction gearbox through the use of a jaw coupling. The gearbox is then attached to a drive plate that is connected to the gearbox's output shaft. Here you see a mounting for a Hall effect sensor on the inside of the drive plate, as well as the trigger magnet used to measure the RPM of the gearbox's output shaft. A secondary drive plate is attached to the primary drive plate and has the connection for the linkage arm that will actuate the gust vanes. Here we see the secondary drive plate, which has a set of holes that will determine the maximum gust vane angle deflection. At this setting, shown here, the gust vanes will deflect approximately 12 degrees in either direction. The secondary drive plate is attached to the long drive rod, which you see here. This drive rod can be adjusted for length based on the adjustment nuts at the top and the bottom. The long drive rod is connected to 2 actuating arms, which are connected to each other with heim joints. These actuating arms are splined and attached directly to the drive shaft of the gust vanes. Here's a closer look at the gust vane spars with a quarter for reference. As you can see, the spars are made of machined sections of metal. On one end of each spar piece is a splined broach to accept the drive shaft, as well as 2 grooves to accept the previous spar's tongue extensions. On the other end, you see the tongue extensions of each spar piece that feed into the subsequent spar piece. As you can see, not all spar pieces are broached to accept the spline shaft. Only the ones on the ends and in the middle require the broaching. Here's a close-up of the gust vanes. The spline shaft runs the full length of each vane. The vanes are a 0015 symmetrical airfoil cross-section made out of FAS hickory that has been CNC'd to the appropriate shape. A metal spar runs the entire length of each vane and provides bending and torsional stiffness during use. As you can see, the ends of each vane terminate inside of the tunnel's boundary layer. Here we see the control panel for the wind tunnel. Note that the 3 screens on this control panel are not used during testing. Only the 2 on-off triggers, the switch and the button to the left of the fan speed, are used to turn the motor and the tunnel VFD on or off. The knob on the right controls the speed of the tunnel. Turn the knob to the right to increase the tunnel speed and to the left to decrease. On the Aero FMS acquisition software, you can see the dynamic pressure and free stream speed of the tunnel. This is what you use to collect your test data for Q and V infinity.
The need for the sensors is because the Cal Poly Pomona low-speed wind tunnel does not currently have a flow visualization capability. Therefore, we need to use sensors to be able to measure what actually is going on inside of the wind tunnel. The need for it is also for a health and accuracy monitoring system. We would like to be able to measure the vane position and frequency and measure the gust magnitude and the frequency of the gust, and be able to compare that against known values to see if the system's acting accordingly. If the data does not match up with the calibrated measurements, then we know there's a problem in the system and it must be corrected. Also, we would like to be able to correlate the motor frequency to the vane frequency and to the gust frequency. That way we will be able to fully characterize the gust flow that is happening inside of the wind tunnel and how it will interact with future models. Here we have our encoder, which is located on the backside of the wind tunnel. The encoder is fastened to the wind tunnel wall by the use of this mounting bracket. The encoder shaft is machined down into a D shape. This D shape allows for the encoder shaft to be inserted into this splined axle rod. The encoder shaft is fastened to the axle rod with the use of a set screw. This allows the rotational force of the axle rod to be translated to the encoder. The encoder then transmits that signal in the form of a PWM signal here in pin 1, and the rest of the pins are located subsequently to the right. Here we have our Hall effect sensor. The Hall effect sensor is located on this mounting bracket, which is approximately 3/8 of an inch away from the drive plate. The reason it is 3/8 inch away from the drive plate is due to the magnetic field. The magnet must be at a minimum distance away from the Hall effect sensor to activate the latching mechanism inside of the Hall effect sensor. As the magnet passes the Hall effect sensor sends a high signal, and then as the magnet retreats off of the Hall effect sensor, it is a low signal which is sent in the form of a voltage to our data acquisition system. Here we have our alpha beta probe. Our alpha beta probe is located inside of the wind tunnel, which is mounted to the sting of the wind tunnel by the use of this bracket. The alpha beta probe consists of 2 vanes. There is the alpha vane, which is located on the back side, and the beta vane, which is located on the top. The beta vane will not be used in this experiment. The alpha vane contains a potentiometer, which, as the angle of attack of the vane increases or decreases, the resistance changes, which corresponds to a voltage which is sent to the data acquisition system. Also contained in the alpha beta probe is pressure ports. In the nose of the probe is a dynamic port, and at the top is a static port. The static and dynamic ports are used to measure the pressure inside of the wind tunnel. The pressure transducer, which is located right here, only for demonstration, which during normal operational activity is located underneath the wind tunnel and on the back side. The pressure signal is then sent to the carrier demodulator. The carrier demodulator must be calibrated using the 0 and span settings before the test begins. The carrier demodulator converts the pressure differential into a voltage, which is then sent to our data acquisition system.
After calibrating each sensor accordingly, a data acquisition system, the NI-MIDAC, was used to acquire data from the various components on the wind tunnel. The NI-MIDAC processes differential inputs in the form of analog or digital signals. Incoming analog signals must remain within a voltage range of plus or minus 10 volts or plus or minus 2 volts if DC coupling is required. The digital signal input and output ports seen here may take in voltages between 0 to 5 volts. However, digital signals were not required for our purposes, so we will focus on the analog channels. Notice that the analog input and output channels are able to process a total of 2 signals. Thus, the signals from the encoder and potentiometer will be processed using one MIDAC, while the Hall effect and pressure transducer signals will be processed on another MIDAC unit. Both data acquisition systems will run simultaneously to acquire data within the same time frame. To accommodate for a change in the type of data acquisition system used in the future, a single power supply was externally connected to each sensor rather than using the power supply capabilities of the MIDAC system. Now let's take a look at each sensor in greater detail.
Sensors and all electronics typically have a data sheet which best describes the way a sensor should be used and operated. Let's take a look at the data sheet for the encoder that we will be using. We are using a Borns EMS22P50 non-contacting PWM encoder. The part number is located on the back of the sensor where the pins are. Looking at the data sheet and the part number, we can tell a number of things from this encoder. Specifically, in the last 3 digits of the part number, we can see that the 5 represents that this sensor operates on 5 volts DC power, and the P tells us that the sensor outputs a PWM signal. The middle number describes the shaft size, and the last part of the part number describes the sensor's resolution. Now, different products have different codes with various meanings, so read and understand your sensor's data sheet before you begin. The resolution for this sensor is 1024 points per revolution. You can think of this like the second hands on a clock. The seconds hand moves 60 times in 1 revolution. That is 60 times in 360 degrees, or 60 ppr. That's points per revolution. Therefore, the encoder has 1024 points in 1 revolution of 360 degrees. Now let's talk about the PWM signal and what it means. The PWM, or pulse width modulation, is a signal that resembles a square wave whose pulse is modulated, which means that the signal is turned on and off really fast. The result is an average voltage that is supplied from a sensor. The way it works is best understood by looking at the duty cycle of a square wave. The duty cycle tells you how long a signal is on high and how long it's on low. A low duty cycle will result in a lower power because the duration the power is off is longer than it is on. Essentially, the duty cycle just changes the width of the pulse. So a duty cycle of 0% would yield an average voltage of 0, whereas a duty cycle of 100% would yield the maximum voltage supplied to the system. So a 50% duty cycle on a 5 volt system will result in an average voltage of 2.5. So what does the resolution mean with regards to the PWM signal? So for this sensor, we have a resolution of 1024 ppr with a minimum pulse of 1 microsecond and a maximum pulse of 1024 microseconds. This means that the minimum pulse width corresponds to 1 over 1024. That is equal to 0.0009765. Multiplying that by 100% will give the minimum duty cycle 0.09765% for this sensor. The period of the signal is 1025 microseconds, and the frequency of the signal is calculated as the inverse of the period, that is, 1 divided by 1025. If you're going to record the PWM signal with a DAC system, you're also going to need to know how to program timers and counters. This process can be extremely complicated for beginners. If you are not familiar with timers and counters, the other option is to turn the PWM signal into an analog signal. This is done by incorporating a low-pass filter provided in the datasheet. Now this sensor isn't going to come with a filter, so you have to make it yourself. Now this filter was built using a breadboard, and you can also use the recommended resistors and capacitors. However, in order to minimize noise, larger resistance and capacitance is recommended, which will increase the filtering and provide fewer ripples in the data. Using larger resistors and capacitors will cause the signal to lag in response time. The minimum resistance for R1 and R2 as stated by the datasheet is 4.7 kiloohms. However, we chose resistors with 5.5 kiloohm resistance. 10 microfarad capacitors were used for C1 and C2. A closer inspection of the filter on the breadboard will reveal that the resistors are connected in series and the capacitors are connected in parallel. The filter converts the PWM signal to an analog signal by calculating the average voltage. The average voltage tells the user what position the shaft of the encoder is at relative to absolute 0 degrees and 360 degrees.
After acquiring encoder signals at several speeds and frequencies, the data was loaded into MATLAB. Tests were ran at 50 feet per second and 30 Hz, 30 feet per second and 60 Hz, and 100 feet per second at 30 Hz. We also included the slope given in the datasheet to be able to determine position from the encoder voltage. One of the changes that was made to the data was to zero out the time. Our data acquisition system encounters a glitch during data logging that causes major discrepancies in time. For example, the time shows 0.5 seconds during the beginning of the data logging, and then it suddenly escalates to 80 seconds. This is the reason that the time must be calibrated to 0. The encoder signals were converted to position by subtracting the measured voltage by an initial voltage recorded at a 0 degree deflection angle, and then divided by the slope. This calibration allows the encoder to record accurate voltages. Now we are ready to analyze the data by plotting deflection angle versus time. To better visualize the position of the encoder, we zoom into a time frame of 5 seconds. Looking at the Gust vein angle of attack, it appears that the veins have a positive angle of attack of about 7 degrees, while the negative angle of attack has a maximum deflection angle of about 10 degrees. Also notice that the encoder position does not oscillate about 0 degrees, but instead about 5 degrees. A hardware error was discovered in unexpected movement of the encoder within the spline shaft rod, which resets the encoder 0 position. To determine the average frequency of the encoder, a simple calculation was performed to determine the cycles per time of the signal. For this particular test, there are 6.5 cycles per the 5-second time frame, which in turn gives us a 1.3 Hz frequency.
There are 3 types of Hall effect sensors: linear, latching, and non-latching. The sensor used for this system is a US 1881 latching Hall effect sensor. A Hall effect sensor is a transducer that provides an output voltage when it senses a magnetic field. A latching Hall effect sensor means that once the trigger is engaged, it remains engaged and will not unlatch until a magnetic force of opposite polarity is sensed. A similar example of this is a light switch, where it can be either on or off. This means that the signal's voltage is changed from low to high when a magnet passes by, just like a person flicking the light switch on. If the north pole of a magnet turns the sensor on, then the south pole of the magnet turns the sensor off, and vice versa. When the US 1881 is triggered, the output signal voltage will be equal to the source voltage, which in this case is 5 volts. When it is unlatched, it will drop to ground or 0 volts. To get a better understanding of this idea, this breadboard shows how the US 1881 was connected. The sensor comes from the distributor already calibrated and cannot be recalibrated. Referring to the datasheet, it is important to realize that at least a 10 k ohm resistor is recommended for use with this Hall effect sensor. It is placed in parallel between VDD and the signal port. As you can see, an LED is in series to indicate when the Hall effect sensor latches and unlatches. As one side of the magnet passes next to the sensor, the LED turns on, representing the 5 volt signal. The light stays on, showing that it is a latching Hall effect sensor. To unlatch or turn off, it would require a magnet with the opposite polarity to pass by, changing it to its low signal state. Due to the nature of the dry plate material and the strength of the magnet used, our Hall effect sensor only required one magnet to turn it on and off. The steel used for the dry plate contains a large amount of iron. Because of this, the dry plate itself became magnetized. Therefore, as soon as the magnet retreated from the Hall effect sensor, the sensor encountered reverse polarity and unlatched back to a low signal. Essentially, the dry plate became our second magnet. The end goal of the Hall effect sensor was to measure the revolutions per second of the output shaft on the gearbox. A data acquisition system recorded when the switch was on and when it was off. Therefore, it is directly related to the motor's frequency of rotation. This is done by focusing on the data collected for 1 second of the time history plot and counting the number of spikes during this duration. The number of spikes will reveal the motor's frequency of rotation in revolutions per second. The data collected from the Hall effect sensor was analyzed in MATLAB. Unfortunately, the results showed an abnormal pulsing pattern. The expected pattern was an evenly distributed pulsing signal. Looking at this time domain plot, when the magnet was over the sensor, a 5 volt signal was produced, represented by the spikes. However, as the revolutions of the dry plate increased, the Hall effect sensor used did not have a fast enough response time to capture every moment the magnet passed by. As a result, the data collected did not represent the actual RPM of the drive plate. When the VFD was operating at a constant 10 Hz setting, the drive wheel was expected to be at an RPM of about 55, but the Hall effect sensor only recorded approximately 25 revolutions per minute.
In order to calibrate the alpha probe, we need to correlate the voltage being recorded through the DAC system to the probe angle of attack. To do this, we use a digital angle finder. The angle of attack and the potentiometer's output voltage are recorded in unison at multiple angles of attack. At least 3 data points are needed to properly correlate this data. However, 6 data points are recommended. The 6 data points are used to generate a calibration plot of angle of attack versus voltage. The equation for the best fit line, shown here, is then solved for x. Now x represents the angle of attack and y represents the measured voltage from the potentiometer. This equation can be used to convert any voltage from the potentiometer recordings into angle. That is how you calibrate the alpha probe. To analyze the alpha beta probe data, we'll first look at a time history plot. So this plot shows on the horizontal axis time and voltage on the vertical axis. Wait, did we forget to convert voltage to angle? Oh, well, let's go back and do that using the equation from the calibration chart. Okay, now we can look at a time history plot where time is on the horizontal axis and angle in degrees on the vertical axis. So the first thing we notice from this plot is the magnitude of the angle of attack. From this plot we can see that we are getting a maximum angle of deflection on the probe of about a half a degree. Okay, cool. So now let's take a look at and find the frequency of oscillation. So how do we do that? Well, the easiest way to do that is to sum the number of cycles in this plot and divide by the time period.
This is a Pace Engineering Company KP15 pressure transducer. This particular one has interchangeable diaphragms, but for this experiment, a diaphragm rated up to 1 psi differential pressure is used. The transducer has a stagnation pressure port that we are using to link to the pitot-static tube to receive airflow. The transducer also has a static pressure port that we are using to detect the atmospheric pressure. In our case, it is linked to the top port of the pitot-static tube. The pressure transducer uses a piezoresistive strain gauge that outputs a signal when it receives a differential pressure. A strain gauge is a resistor that changes resistance when deformed. When a power is applied to the pressure transducer, a signal can be read by a measured voltage. What the pressure transducer is connected to is the Valentine CD15 carrier demodulator. This device can output a maximum of negative 10 volts DC. The transducer has a 0.005% per degree Fahrenheit zero shift specification that needs to be adjusted because of temperature change. This demodulator has two settings called 0 and span. The 0 is used to set a reference 0 for reading data. Linking the demodulator to a data acquisition can do this. To set the 0 reference, the 0 adjustment is rotated counterclockwise or clockwise until the value without load is now equal to the neutral point. The other setting is the span, which is used to adjust range of values. This ranges from 0% to 100% of the signal, 10 being 100% of the signal, then 0 stops all signal. This should always remain at 10 prior to any adjustment. Now that the calibration of the demodulator has been performed, the calibration of the pressure transducer can occur. Once the connections are verified, you can proceed to obtain values. The calibration starts by having a known pressure applied to the stagnation port. While the stagnation pressure is applied, the voltage is read from the data acquisition system. This voltage is recorded with respect to the pressure applied. Take the information gathered and plot the data seen onto a graph and extract the best fit linear line. Also determine the r² of the line. This must equal approximately to 1, and if it doesn't, perform the calibration procedure once again. The last verification is to check if the angles of the vanes are at 0 degrees prior to the start of the test. This ensures correct free stream velocity. For our system, this is done by measuring the height of the trailing edge relative to the base of the test section of the low-speed wind tunnel. After a steady frequency is set, the logging feature is activated on the data logging system. Stop the log once a minute has passed and then process the data by graphing the points against time. What is seen in the graph is voltage versus time. This can be converted over to velocity by using the equation for equivalent airspeed and conversion of the pressure transducer. Plotting this information gets velocity versus time. Notice the noise picked up by the data acquisition system. What causes this is an unconditional power source from either the sensor equipment or the data acquisition system. The frequency can be assumed by measuring the time difference from peak to peak, but not with enough accuracy to be able to guarantee the frequency. Use a power conditioner for testing equipment is also recommended. What this will do is act like a filter for voltage spikes. This will help create a more controlled testing environment for the pressure transducer and other testing equipment.
This brings us to the conclusions and recommendations segment. As seen from each of the sensors, there was a large amount of noise in the signal. This noise was contributed by the wall outlet power supply, and the disturbances from that caused an error in our signal. We discovered this as one of the laptop batteries, which was recording data, was about to die. We plugged in the power supply for the computer and we saw a large spike in the data. We investigated this. We found that as the power supply was unplugged, the noise was reduced. But when we plugged the power supply back into the computer, the noise reappeared. That is how we concluded our result. The encoder had an error in the data due to the set screw becoming loose. The encoder then moved inside the bracket tree. The alpha probe, however, was about the best data we had recorded. The frequency of the alpha probe was matched to the encoder frequency. This obviously is a good sign. The Hall effect sensor, however, was not very accurate. Due to the low sensitivity of the Hall effect sensor, the results were not conclusive. The RPM, which was calculated, was not the same as what was recorded from the Hall effect sensor. Recommendations for future use. Recommendations would be to use sensors with higher sensitivity, and we would like to use sensors that are designed for this specific application. Also, the encoder used was a center mount encoder. We would prefer to use a 3-prong mount encoder to reduce the twisting motion of the encoder. The last thing would be to condition the power supply. By conditioning the signal of the power supply, we would be able to reduce noise and therefore our data would be better.
Thank you for your time. We hope you learned something. If you have any questions or comments, feel free to post them in the comments section below. We'd love to hear your input.
I don't hunch over like this. I don't do the T-Rex thing.
You do the chicken.
Justin, get out of here.
No, move to the, yeah, keep moving that way. Okay, I can
Just
see.
fix that thing and I'll take care of their ass. Drive it like you stole it.
Oh, I gotta pay for it.
No, pretend you stole it.